Before we can begin to understand the strange and beautiful world of string theory, we must first take a step back. We must look at the puzzle that physicists have been trying to solve for over a century, a puzzle with two powerful pieces that just won't seem to fit together. Let's start with the familiar. For most of human history, we saw the universe as simple. Objects moved, fell, and collided in predictable ways. We watched the sun rise, the tides ebb and flow, and apples drop from trees. All of this seemed to obey laws we could understand intuitively. Then came Isaac Newton, who in the 17th century gave us the laws of motion and universal gravitation. His equations explained the falling apple, just as well as they explained the orbits of planets. The universe, it seemed, was a kind of giant machine, a celestial clockwork governed by a few elegant rules. This view held strong for centuries, that is until the early 20th century, when cracks began to show. Enter Albert Einstein. In 1905, Einstein introduced his special theory of relativity, revealing that time and space were not fixed, but relative to the observer. Then in 1915, he took it a step further with his general theory of relativity, a new theory of gravity. Einstein showed that gravity wasn't really a force, as Newton thought, but rather the result of space-time curving around massive objects. Imagine placing a bowling ball on a trampoline, the fabric curves, and a marble placed nearby will roll toward the heavier object. That's gravity, according to general relativity. Suddenly, the universe became far more dynamic and far more mysterious. Einstein's theory worked beautifully at cosmic scales. It predicted the bending of starlight around the sun, the expansion of the universe, and even the existence of black holes. These were not speculations, they were confirmed by experiment. But something else was stirring at the other end of the scale, the quantum realm. Around the same time Einstein was reshaping our understanding of space and time, physicists like Max Planck, Niels Bohr, and Werner Heisenberg were exploring the behavior of the very small atoms and subatomic particles. And what they found was weird particles that acted like waves, energy that came in discrete packets, or quanta, an electron that could exist in many places at once, until you looked at it. This was the world of quantum mechanics, and it was nothing like classical physics. Where Einstein gave us elegant deterministic curves of spacetime, quantum mechanics gave us uncertainty, probabilities, and a reality that didn't quite settle until it was observed. But again it worked. Quantum theory explained chemical bonds, radioactivity, the glow of stars, and the electronics that run our modern world. It's arguably the most successful scientific theory ever developed. There was just one problem. These two great pillars of physics, general relativity and quantum mechanics, refused to play nice with each other. Whenever physicists tried to apply quantum principles to gravity, say to describe what happens inside a black hole or during the birth of the universe, the math broke down. Equations exploded into infinities. Space and time became meaningless. Something was missing. A deeper framework was needed. Something that could unify the very large with the very small, the smooth curvature of spacetime with the jittery quantum foam. This search for a unification became the holy grail of theoretical physics. Imagine trying to write a book with two different languages, one elegant, flowing, classical, the other chaotic, uncertain, probabilistic. Each makes sense on its own, but put them together, and the story falls apart. What physicists needed was a universal language, something that could bridge the vast with the tiny, the cosmic ballet of galaxies, and the twitching chaos of particles. And it's in this context, out of this problem, that string theory was born. But string theory didn't begin as a solution to this problem. In fact, it started almost by accident. In the 1960s, physicists were trying to understand the strong nuclear force, how protons and neutrons stick together in the nucleus. In the process, they stumbled onto a strange mathematical formula that described the behavior of particles not as points, but as if they were tiny vibrating strings. At the time, it was considered a mathematical curiosity, a dead end. But some physicists looked deeper and realized that this stringy description had a hidden gift. It naturally included a particle that behaved exactly like the graviton, a theoretical particle that would carry the force of gravity. This was no coincidence. What they had found was a potential quantum theory of gravity. And so slowly, string theory transformed from a footnote into a frontrunner. It proposed that everything, all particles, all forces, even space and time, might emerge from the vibrations of tiny one-dimensional strings. Each vibration, like a different note on a violin, corresponds to a different particle. Mass, charge, spin, All the traits of a particle are just the music of the string. In this picture, the universe isn't made of dots, but of melody. We are standing on the edge of a new way to see the universe. A vision where the cosmos is not made of particles, but patterns. Not of things, but relationships. Where the fabric of reality is not solid and static, but dynamic, ever shifting, ever vibrating. But to understand this vision, we need to go deeper. In the chapters ahead, we will explore the journey that took physics from the cold equations of Newton to the shimmering landscapes of string theory. We will meet the players, trace the breakthroughs, and wrestle with the mysteries. We will go to the smallest scales and the highest dimensions. We will ask, is string theory the final theory, or just another chapter in the great story of science? The prelude is over. The strings are waiting. Let us begin. To understand how string theory emerged, we need to look more closely at the physics of the 20th century, particularly the successes and limitations of the standard model of particle physics. Imagine for a moment that the entire visible universe, all the stars, planets, galaxies, and everything on Earth, is made of just a few basic building blocks. That's not just imagination, it's the central idea behind the standard model. At its heart are elementary particles, like quarks and leptons, and the forces that act between them. Quarks combine to form protons and neutrons. Electrons orbit atomic nuclei. Alongside them are other exotic particles, and holding it all together are three fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. Each of these is carried by a special kind of particle called a gauge boson. For example, the photon carries the electromagnetic force. It's an elegant theory, and it works astonishingly well. With it we can explain how the sun burns, why atoms are stable, and even how particles behave inside the Large Hadron Collider. In 2012, the discovery of the Higgs boson filled in one of the last missing pieces of the puzzle. But as powerful as the standard model is, it has a major blind spot: gravity. The force that governs the motion of planets, and the shape of the universe itself, is completely absent from the model. That's because gravity is described by Einstein's general relativity, which is a theory about space and time, not particles and fields. When physicists try to plug gravity into quantum field theory, the results don't make sense. The equations produce infinities that can't be cancelled out, and predictions break down. It's like trying to fit a square peg into a round hole. On top of this, the standard model has other shortcomings. It says nothing about dark matter, which makes up most of the mass in the universe. It can't explain dark energy, the mysterious force driving the universe's expansion, and it treats some constants like particle masses and force strengths, as if they were just arbitrarily chosen. Physicists began to suspect there had to be a more fundamental theory, one that would explain not just how particles behave, but why they exist at all, and why the universe has the laws it does. This led to many speculative ideas, from supersymmetry, which proposes a partner particle for every known one, to grand unified theories, which try to merge the strong, weak, and electromagnetic forces into a single framework. But all of these approaches eventually ran into mathematical difficulties, or they just lacked experimental support. Then came an idea so radical that it changed the shape of the conversation. What if particles aren't points at all? What if they're tiny vibrating strings? This idea didn't come out of nowhere. In fact, it emerged from an entirely different problem, one that had nothing to do with gravity, and that brings us to the curious, accidental birth of string theory. The story begins not with gravity or quantum mechanics, but with the strong nuclear force, the force that binds protons and neutrons together inside atomic nuclei. In the 1960s, physicists were trying to make sense of the growing zoo of subatomic particles being discovered in particle accelerators. There were mesons, baryons, and all sorts of resonances, each with different masses and lifetimes. It was chaotic, and no one understood the underlying pattern. In an attempt to bring order to this mess, an Italian physicist named Gabriele Veneziano found a strange mathematical formula in an old math book. When he applied it to the scattering of certain particles, it fit the data perfectly, but no one really knew why. Soon after, other physicists realized that this formula looked like what you'd get if particles weren't zero-dimensional points, but rather tiny one-dimensional strings. The vibrations of these strings could account for the many different particles seen in experiments, much like how different vibrations on a violin string produce different musical notes. The idea was compelling, but it didn't quite catch on at first. The new theory predicted a massless spin 2 particle, which didn't fit into the picture of the strong force. It was a nuisance, an unwanted feature. But a few bold physicists took a second look. A massless spin 2 particle is exactly what you'd expect if you were trying to describe gravity in quantum terms. That annoying artifact, it might actually be a graviton, the theoretical quantum particle that carries the gravitational force. Suddenly, this strange little theory, originally meant to explain the strong force, had accidentally stumbled upon a possible quantum theory of gravity. This was revolutionary. It meant that string theory wasn't just a theory of particles, it could be a theory of everything. Unlike point particles, strings don't have sharp edges. They spread out in space, which softens the violent quantum fluctuations that usually wreck calculations involving gravity. In other words, string theory could naturally avoid the infinities that plagued other quantum gravity approaches. And that's not all. As physicists explored the theory further, they discovered more surprises. Strings could be either open like a line, or closed like a loop. Their vibrations could describe not just gravitons, but also photons, gluons, quarks, potentially every fundamental particle we know. However, the theory came with strange demands. First, it only worked if the universe had more than the familiar 4 dimensions of space and time. In fact, it required 10 dimensions, 9 of space and 1 of time. Later versions of the theory would even suggest 11. Second, for consistency, the theory required a property called supersymmetry. That meant every known particle must have a partner, a superpartner. We haven't yet observed these partners in experiments, but they remain a key prediction of many versions of string theory. Despite these oddities, the potential was too great to ignore. Physicists began to take the idea seriously. By the 1980s, string theory was no longer a fringe idea. It was at the forefront of the search for a unified theory. Still, there was a long road ahead. As more versions of string theory emerged, 5 in total, it became clear that understanding how they fit together would require another leap. That leap would come in the 1990s, when string theorists discovered that all 5 theories were connected. They were not rivals. They were aspects of a single deeper theory. But that's a story for later. For now, it's enough to know this string theory began as a failed attempt to describe the strong force. By accident, it offered something far more profound, a way to unify all the forces of nature, to merge the quantum and the cosmic, to describe everything as vibrations on tiny strings. It was no longer just a theory of particles, it was becoming a theory of reality itself. By the late 1980s, string theory had grown from a speculative curiosity into a serious candidate for a theory of everything. But as physicists dove deeper, they encountered a strange and unexpected problem. Instead of a single unified theory, they found 5 different string theories. Each one described the universe in its own way. They had different mathematical structures, different kinds of strings, different symmetries. Some had only closed strings, while others allowed open strings. Some included supersymmetry in a particular way, others in another, but all 5 were internally consistent. None could be dismissed as obviously wrong. This was troubling. Physics seeks simplicity. The idea of 5 fundamental theories of everything didn't sit well with anyone. If string theory was truly the final theory, why should there be 5 versions? The 5 theories were named based on their mathematical structure. Type 1. This theory includes both open and closed strings and incorporates a specific kind of symmetry involving 2 types of strings. Type 2. A theory with only closed strings. It is non-chiral, meaning it does not distinguish between left and right-handedness in its mathematical laws. Type 2b. Another theory of only closed strings, but this one is chiral. It does distinguish between left and right-handed interactions. Heterotic OA hybrid theory that combines different aspects of string behavior. It uses a peculiar mathematical structure related to symmetry groups in particle physics. Heterotic A, another hybrid theory, similar to the previous, but built on an even more complex symmetry group. This version is especially interesting because it can in principle give rise to a universe similar to ours. Each of these theories required 10 dimensions to be mathematically consistent, 9 spatial dimensions and 1 of time, and each was supersymmetric, meaning it included partner particles for every known particle. Still, 5 final theories were 4 too many. This led to a shift in focus. Physicists began looking for deeper connections. They wondered, could these 5 theories be just different perspectives on the same underlying truth? This idea gained traction in the 1990s, in what came to be known as the second superstring revolution. A key breakthrough came from an unexpected direction: duality. In physics, duality is a kind of mirror symmetry. 2 different theories might appear unrelated, but when you transform certain quantities, like swapping strong forces for weak ones, or changing the size of a dimension, one theory transforms into another. This idea, radical as it sounds, had real power. Imagine 2 hikers climbing opposite sides of a mountain. From their vantage points, the mountain looks completely different. Steep cliffs on one side, gradual slopes on the other. But it's the same mountain. Their experiences are different, but the reality is one and the same. Physicists discovered that some of the 5 string theories were dual to one another. Under certain transformations, what looked like one theory turned into another. This hinted that all 5 were simply facets of a deeper, more fundamental theory. That deeper theory wasn't fully understood yet, but it had a name: M-theory. M-theory promised to unify the 5 string theories into a single framework. It predicted that instead of just strings, the universe might also include higher dimensional objects, like membranes, or brains for short. In fact, M-theory seemed to require 11 dimensions, not 10. This was astonishing. The original string theories had emerged from the need to unify quantum mechanics and gravity. Now, as they were unified themselves, they revealed a universe even more rich and complex than anyone had imagined. The extra dimensions in these theories aren't visible in everyday life. According to the mathematics, they are curled up so tightly that we can't detect them. Like the width of a sheet of paper, invisible from far away, these tiny dimensions are hidden in the fabric of reality. Some physicists imagined these extra dimensions as being curled into intricate geometric shapes called calabi-yau manifolds. The shape of these hidden dimensions might determine everything we see: why electrons have the mass they do, why the universe has 3 large spatial dimensions, why particles interact the way they do. And that raises a profound possibility, that the laws of physics we observe are not the only possibility. There may be millions or even billions of different calabi-yau shapes, each giving rise to a different version of physical reality. This is what led physicists to the concept of the string landscape, a vast collection of possible universes, each with different physical laws, all consistent with string theory. But for many, this was troubling. If the theory could describe any universe, how could it predict our universe? If string theory could explain everything, could it really explain anything? This question remains deeply controversial, and we'll return to it in a later chapter. For now, we're left with a remarkable vision, that the 5 string theories are like the faces of a cube. They seem different, but they're part of the same structure. M-theory sits at the center, still largely mysterious, but hinting at an even deeper truth beneath the surface. The journey of string theory is no longer just about unifying particles or forces. It's about unifying theories themselves, and it's opening the door to a multiverse of possibilities. As string theory evolved, so too did its ambition, not just to describe particles, but to redefine what we mean by reality itself. We began with the idea that fundamental particles are not point-like dots, but tiny vibrating strings. But as physicists studied the mathematics more deeply, they discovered something even more exotic: brains, short for membranes, multi-dimensional objects that expanded the landscape of string theory. A string is a one-dimensional object. It has length but no thickness. But nothing in the theory says we must stop at one dimension. In fact, the mathematics allows for extended objects with 2, 3, or more dimensions. These higher dimensional objects, p-branes, where p denotes the number of spatial dimensions, can range from 0 a point to 9. For example, a 0 brane is like a point particle, a 1 brane is a string, a 2 brane is a surface, like a membrane, and higher dimensional branes, 3 branes, 4 branes, and so on, extend in even more directions. One of the most intriguing discoveries came from the realization that our entire universe might be a 3-brane, embedded in a higher dimensional space. That is, everything we experience, our world of 3 spatial dimensions and 1 time dimension, could be confined to a membrane floating in a higher dimensional bulk. In this picture, gravity is different from the other forces. Unlike electromagnetism or the nuclear forces, which are trapped on the brain, gravity can leak into the extra dimensions. This could help explain why gravity is so much weaker than the other forces. It's spread out across a larger volume of space. This idea gave rise to brain world scenarios, where the familiar universe is just a slice of a much larger cosmos. Other brains could exist parallel to ours, each hosting its own universe. These parallel brains might even come close to ours, perhaps only a microscopic distance away, but remain hidden, like pages in a book we cannot turn. This is not just science fiction. The Randall-Sundrum models, proposed in 1999, explored how extra dimensions and brains might be warped in such a way that their effects could be felt even at observable scales. These models suggested new ways to probe extra dimensions in particle accelerators, or through deviations in Newton's law of gravity at short distances. But the deeper consequence is philosophical. If brains and extra dimensions are real, then our conception of space itself must change. The 3 dimensions we move through daily might be just part of a much richer, higher dimensional arena. And within this arena, brains can interact. One of the most provocative ideas in modern string theory is that the Big Bang itself might have been caused by a collision between brains. In these so-called ekpyrotic or cyclic models, the universe didn't begin from a singularity, but from the violent interaction of higher dimensional surfaces. These collisions could create bursts of energy, like our universe, and might even happen repeatedly, leading to an eternal cycle of birth, expansion, and rebirth. In this view, the fabric of reality is not empty space, but a dynamic, ever-changing structure of strings and brains, vibrating and colliding across hidden dimensions. The very concept of dimension becomes more fluid. We're used to thinking of dimensions as static: length, width, height. But in string theory, dimensions can be compactified, curled up so small we cannot see them. They can also be warped, folded, or emerge from more fundamental relationships. In some proposals, space and time are not even fundamental. They emerge from quantum entanglement, or deeper informational principles. This leads to a stunning possibility. Space itself might not be fundamental. It may be a derived concept, emerging from deeper mathematical or quantum processes. In this evolving picture, reality is not made of things located in space. Instead, it is built from relationships, patterns of vibration, and interactions among extended dynamic objects in a vast multidimensional arena. And the more we look, the stranger it gets. As string theorists examined the theory further, they found that strings can split, join, and interact, but so can brains. 2 brains might intersect, exchange energy, or even bind together. The possible interactions are nearly infinite. From these complex dynamics, entire universes can emerge, each with its own laws of physics, determined by how strings and brains are shaped, how dimensions are curled, and how forces arise from the vibrations. At this point, string theory is no longer just a theory of matter and energy. It's a theory of space, time, and existence itself. But it is not without cost. We cannot yet observe strings or brains directly. The extra dimensions, if they exist, are too small to detect. The theory's predictions are subtle and difficult to test. And the number of possible solutions, the string theory landscape, is so vast that we may never find the one that precisely matches our universe. And yet, the theory holds a kind of beauty. Its mathematical consistency, its unification of gravity with quantum mechanics, and its vision of a reality built not of points, but of geometry, vibration, and relationship. It all points to something profound. It suggests that the universe is not static but dynamic, not a set of fixed laws but an evolving tapestry of patterns and resonance. In string theory, the fabric of reality is alive, woven from vibrating strands and shifting brains, shaped by the dance of hidden dimensions. In the next chapter, we'll explore one of the most surprising consequences of this vision, the idea that we may live in a multiverse, a vast collection of parallel realities, each governed by its own version of physics. We'll ask, if our universe is just one of many, what does that mean for science, for prediction, for meaning? The cosmos is far stranger and more wondrous than we ever imagined. For most of history, the universe was assumed to be singular, a lone, majestic expanse of space, time, and matter. But string theory, with its layers of hidden dimensions and countless possible configurations, suggests something radically different. It hints at the possibility of a multiverse, not just one universe, but many, perhaps an infinite number. This idea doesn't arise from science fiction or philosophical speculation. It comes directly from the mathematics of string theory. As we've seen, string theory requires extra dimensions, typically 6 additional spatial dimensions curled up into complex geometric shapes known as calabi-yau manifolds. But here's the key: there's not just one way to curl up these extra dimensions. There are a vast number of possible shapes, each leading to a different version of physical reality. Some shapes produce universes with electrons and photons. Others might produce no stable atoms at all. Some may have strong gravity and weak electromagnetism. Some may lack stars. Some may contain matter made of entirely unfamiliar particles. These different shapes correspond to different vacuum solutions in string theory. Each one represents a distinct way the universe could settle into a stable or semi-stable state after the Big Bang. This vast collection of possibilities is called the string theory landscape. Estimates suggest there could be around 10 to the 10 to the different possible vacua, each describing a unique universe with its own physical constants, particles, and even laws of nature. To put that number in perspective, there are roughly 10 to the atoms in the observable universe. The number of possible string theory universes dwarfs that. So what does this mean? If the landscape is real, then the universe we live in, one with electrons, protons, stars, galaxies, and life, is just one particular region of this landscape, not unique, not central, just one of many. In this view, asking why are the laws of physics the way they are may not have a fundamental answer. Instead, it might be like asking, why is Earth the third planet from the Sun? A question answered by circumstance, not necessity. This is where the idea of the anthropic principle enters the picture. The anthropic principle states that the universe must be compatible with conscious observers. That is, we observe this universe because we live in it, and we can live in it because it happens to support life. If the multiverse exists, if there are billions or trillions of universes, each with different physical parameters, then it's not surprising that some of them would be just right for life. We just happen to live in one of those. This idea is controversial. To many physicists, it feels like giving up. Science has always sought deeper explanations. The idea that our universe is just one possibility among many feels unsatisfying, even defeatist. It threatens to remove the predictive power of science. But others argue that the multiverse is a natural consequence of the theory. If string theory leads to a landscape, and if cosmic inflation, our best model of the early universe, causes space to expand in different regions in different ways, then a multiverse may be inevitable. In such a model, different regions of space undergo different symmetry breakings, settle into different vacuum states, and evolve into entirely different universes, each with its own version of physics. This kind of inflationary multiverse is sometimes called the eternal inflation model. In it, our observable universe is just a bubble in an ever-growing cosmic foam. And here's where things get even stranger. In some models, these universes could be born when brands collide in higher dimensional space. Others suggest universes might tunnel from one vacuum state to another. And in certain versions of quantum mechanics, every possible outcome might actually exist, in parallel. In what's known as the many worlds interpretation, the multiverse is no longer a fringe idea. It's becoming a serious part of modern theoretical physics, tightly woven into string theory, inflationary cosmology, and quantum mechanics. But it leaves us with deep questions. If other universes exist, can we ever detect them? Can we test this idea scientifically? Or is it forever beyond our reach? Some physicists hope that signatures of other universes, such as gravitational waves or anomalies in the cosmic microwave background, might one day be found. Others search for ways to constrain the landscape mathematically, to find rules that narrow the field of possible universes to a manageable few. But many acknowledge that if the landscape is real, then we may have to rethink what it means to do science. Instead of seeking unique predictions, we may need to understand probability in a multiverse, why we're more likely to find ourselves in one kind of universe than another. This leads to a shift in perspective, from seeing the laws of nature as fixed and absolute, to seeing them as environmental, dependent on the context in which a universe finds itself. And it raises one final question. If our universe is just one of many, what does that say about meaning, about significance, about our place in the cosmos? Some find it humbling, others find it thrilling, but few remain unmoved. The idea of the multiverse, of countless realities beyond our own, is not just a scientific proposition, it's a philosophical and even spiritual challenge. It forces us to reconsider what it means to be alive in a cosmos so vast, so varied, and so filled with possibility. In the next chapter, we'll return to the heart of the theory and ask, is string theory testable? Can it be proven or falsified? And if not, can it still be called science? Because if string theory is to fulfill its promise as a theory of everything, it must face its greatest challenge yet, the challenge of evidence. String theory is one of the most ambitious ideas in the history of physics. It attempts to unify all the fundamental forces of nature into a single framework. It aspires to explain every particle, every interaction, and even the fabric of space and time itself. But for all its elegance, complexity, and mathematical consistency, string theory faces one towering question: can it be tested? In science, testability is the foundation. A theory must make predictions, statements about what we should observe under specific conditions. If a prediction turns out to be wrong, the theory is falsified. This is what separates science from philosophy, myth, or speculation. String theory so far has not produced any definitive testable predictions that can be confirmed or refuted by experiment. This is not because the theory lacks structure, it has a rich, well-defined mathematical form. The challenge lies in its scale. The typical length scale of a vibrating string is on the order of the Planck length, about 10^12 meters. That's over a trillion times smaller than the diameter of a proton. At that scale, quantum gravity effects dominate, but we are nowhere near able to probe such distances directly. Our most powerful particle accelerator, the Large Hadron Collider, operates at energy scales of a few tera-electron volts TeV. To detect the direct effects of string theory, we'd need energies around the Planck energy, which is roughly 10^1 GeV, far beyond anything we can produce, now or in the foreseeable future. So how do we test a theory that operates so far beyond experimental reach? There are a few possible avenues. 1. Low-energy predictions. Some physicists hope that string theory might still leave traces at lower energies, subtle imprints of its higher dimensional structure, or hidden symmetries. For example, string theory predicts supersymmetry, a symmetry between bosons and fermions. If supersymmetry is correct, every known particle has a heavier superpartner. These superpartners could in principle be discovered in particle accelerators. However, despite decades of searching, no superpartners have been found. This doesn't disprove string theory, but it does constrain the kinds of models within the theory that can describe our universe. Another possibility is the discovery of extra dimensions. In some string scenarios, the extra dimensions might be large enough to produce measurable effects, like tiny deviations in Newton's law of gravity at very short distances. So far, such deviations have not been observed. 2. Cosmological clues. The early universe, moments after the Big Bang, may have been governed by energies close to the string scale. That opens the door to cosmological tests. Physicists study the cosmic microwave background (CMB), the afterglow of the Big Bang, for signs of unusual patterns, such as non-standard inflationary behavior or imprints of brane collisions. These effects, if found, might support certain versions of string theory. Gravitational waves, too, could carry signatures from the earliest moments of the universe. A distinctive pattern in the polarization of primordial gravitational waves could in theory provide evidence for string-based models of inflation, but so far the data is inconclusive. 3. Mathematical consistency. String theory is often defended not by its predictions, but by its internal logic. It's the only known theory that unites general relativity with quantum mechanics in a consistent mathematical framework. This is not a prediction, but it is a powerful argument. Other attempts to quantize gravity, such as loop quantum gravity, remain mathematically promising, but less complete. String theory's consistency in 10 or 11 dimensions, its built-in inclusion of gravity, and its rich structure of symmetries and dualities all suggest that it may be on the right track. Some physicists argue that this mathematical coherence is evidence enough that we should trust the theory because it fits so naturally into the structure of known physics. But this, too, is controversial. 4. The landscape problem. As discussed in the previous chapter, string theory appears to permit a vast landscape of possible universes, perhaps 10 theory or more. This makes it incredibly flexible. It can accommodate almost any set of physical constants, any particle spectrum, any outcome. But that flexibility is a double-edged sword. If a theory can explain anything, it risks explaining nothing. If every possible universe is allowed, then why this one, why not another? And how can we ever test which vacuum corresponds to reality? Some argue that this makes the theory unfalsifiable, and therefore unscientific. Others counter that we simply haven't understood the selection mechanism yet, that there may be deep principles we've yet to uncover that explain why our universe is the way it is. 5. Indirect support. Even if string theory can't be directly tested yet, it has produced important mathematical insights. It has contributed to fields as diverse as black hole thermodynamics, condensed matter physics, and even pure mathematics. For example, string theory helped lead to the ADS-CELES-CFT correspondence, a remarkable duality between a theory of gravity in a higher dimensional space, anti-de Sitter space, and a quantum field theory on its boundary. This has provided tools to study strongly interacting systems in ways previously impossible. In this sense, string theory has predicted useful ideas, even if not directly testable phenomena. But this raises a deeper question: should physics be guided by mathematical beauty and internal consistency, even if direct tests are currently out of reach? Or must a theory be empirically verifiable to be meaningful? This tension is at the heart of the current debate. String theory stands at a crossroads. It is vast, deep, and incredibly rich, but it remains, for now, untested. Some physicists remain passionate advocates, convinced that the theory's depth and elegance are signs of its truth. Others are skeptical, arguing that without clear predictions and falsifiability, string theory risks drifting away from science into the realm of metaphysics. Still others adopt a more patient stance, acknowledging the difficulties, but recognizing that the history of science is full of long waits. It took centuries to test the predictions of general relativity. It may take centuries more to probe the Planck scale. For now, string theory remains a bold and beautiful vision, a theory not of what we see, but of what might be. In the final chapters, we'll explore what this vision means, not just for physics, but for our understanding of reality and of ourselves. Because whether or not string theory is right, it has already changed the way we ask the most profound questions of all. String theory was born from physics. It was crafted to solve problems, to unify the forces of nature, to answer the lingering puzzles left behind by quantum mechanics and general relativity. But over time, as the theory expanded and evolved, it began to venture into deeper territory once reserved for philosophers. What is space? What is time? Are the laws of nature fixed or contingent? Is our universe the only one? What does it mean for a theory to be true? These are not just scientific questions. They are philosophical ones, and as string theory has grown more ambitious, its implications have increasingly invited both fascination and critique from thinkers outside the realm of physics. 1. The nature of reality. Perhaps the most profound philosophical implication of string theory is its redefinition of what reality is made of. We used to think the universe was composed of point particles moving through space and time. String theory replaces those points with tiny vibrating strings, and adds layers of hidden dimensions and dynamic geometry. Branes, dualities, emergent space. These are not just technical concepts, they are claims about the fundamental structure of existence. If space and time are not fundamental, if they emerge from deeper quantum processes or information-theoretic structures, then our most basic intuitions are wrong. Reality is not what it seems. This realization has deep echoes in philosophy. The idea that what we perceive is merely a projection or an emergent phenomenon can be traced back to Plato's cave, to Buddhist metaphysics, to Descartes' skepticism. String theory, despite its mathematical rigor, seems to circle back to the oldest philosophical questions: what is really real? What lies beneath the surface? 2. Mathematics and physical truth. One of the most striking aspects of string theory is its reliance on mathematical beauty. Many of its advocates are drawn to its internal consistency, its elegant equations, and its deep connections to geometry and symmetry. But this raises a question: should mathematics guide our understanding of the universe, even in the absence of experimental evidence? Historically, many successful theories, like Maxwell's equations or Einstein's relativity, were inspired by a sense of mathematical elegance. But they were also tested and confirmed. String theory, so far, has not passed that second test. This has led some critics to ask, has string theory become too mathematical? Has it crossed the line from physics into pure mathematics, or even metaphysics? Is beauty a reliable guide to truth? The philosopher of science Karl Popper famously argued that a scientific theory must be falsifiable. It must make bold predictions that can be proven wrong. If a theory cannot be tested, it risks becoming pseudoscience, no matter how elegant. Defenders of string theory counter that it is still evolving, that the difficulty of testing it does not negate its value, but the debate continues. 3. The landscape and scientific explanation. Another philosophical concern lies in the string theory landscape, the vast collection of possible universes allowed by the theory. If string theory predicts not one universe but a multiverse of 10 circumflex 500 possibilities, then it becomes hard to explain why our universe is the way it is. The answer becomes, because we live in a universe where the laws happen to support life. This is the anthropic principle, and while it may be logically sound, many physicists find it deeply unsatisfying. It feels like giving up on deeper explanation. It feels like replacing science with statistics and selection effects. Is this still science, or is it a philosophical retreat? Some philosophers argue that scientific explanation must do more than account for what we observe. It must also constrain the range of what's possible. If a theory permits everything, it explains nothing. Others, however, suggest that our notions of explanation must evolve. If the universe is part of a vast multiverse, then our place within it might be understood only probabilistically. That doesn't make the theory wrong. It simply means that explanation must take on a new form. 4. The limits of human understanding. String theory is incredibly complex. It requires advanced mathematics, operates in spaces we cannot visualize, and describes processes that occur far beyond any direct observation. This raises a haunting question: are there limits to what we can understand? We evolved to survive in a three-dimensional world with slow-moving objects. Our brains were not designed to grasp 11-dimensional manifolds or vibrating topological surfaces. Yet through mathematics, we try to reach beyond our evolved limits. String theory may be a glimpse of a reality far beyond what any human mind can truly picture. If so, we may rely increasingly on mathematical formalism, computer simulations, and artificial intelligence to guide our understanding. In this sense, string theory challenges not just our models of the universe, but the very idea of understanding itself. 5. Science or speculation. At the heart of the criticism lies a central concern: has string theory become disconnected from empirical science? There are no direct observations of strings, brains, or extra dimensions. The theory has yet to make unique testable predictions. The landscape problem means that almost any observation can be accommodated within some version of the theory. This makes many physicists uneasy. Some believe that decades of brilliant minds have been invested in a theory that, while beautiful, may ultimately prove unphysical. They worry that string theory has become a kind of intellectual gravity well so alluring that it draws talent and resources away from other promising avenues. Others believe that we are simply in a long, slow phase of theoretical development. They compare it to the early days of quantum mechanics, when speculation outpaced experiment, or to the centuries it took to confirm aspects of Newton's theory of gravity. Whether string theory turns out to be right or wrong, they argue, it has already expanded our conceptual horizon. In the end, string theory is more than a scientific theory. It is a mirror, a reflection of our desire to understand, to unify, to see behind the veil of appearances. It asks us to believe in unseen dimensions, to follow mathematics beyond the reach of experiment, to consider a universe more complex and more strange than anything we have known. It may be right, it may be wrong, it may be a step on the way to something greater, but whatever the case, it has already changed the way we think. It has stretched the boundaries of physics and of philosophy, and in doing so, it has reminded us that the quest for knowledge is as much about asking the right questions as it is about finding final answers. In the final chapter, we'll return to the beginning and ask, what has string theory taught us, and where do we go from here? String theory began as an ambitious attempt to describe the strong nuclear force, but it quickly grew into a grand quest to unify all forces and particles into a single framework. Over the past several decades, It has evolved into one of the most mathematically rich and conceptually daring ideas in physics. Its legacy is profound. Even if string theory ultimately proves incomplete or incorrect as a theory of everything, it has already transformed physics and mathematics in multiple ways. It has introduced new concepts, extra dimensions, branes, dualities, that have expanded the language and tools of theoretical physics. It has inspired connections between gravity and quantum field theory that were previously unimaginable. Its influence extends beyond physics into pure mathematics, giving rise to new insights in geometry, topology, and number theory. The famous ADS-CFT correspondence has provided a bridge between seemingly unrelated fields and has found applications even in condensed matter physics and quantum information. The journey of string theory also reflects the changing nature of physics itself. Today's theories demand mastery of complex mathematics, computational techniques, and interdisciplinary collaboration. The quest for fundamental understanding is increasingly subtle and abstract. What about the future? String theory faces both challenges and opportunities. The lack of direct experimental evidence remains a hurdle. Some physicists are exploring alternative approaches to quantum gravity, such as loop quantum gravity or causal sets. Others pursue phenomenological models inspired by string theory, searching for indirect evidence through cosmology or particle physics. Technological advances, more powerful particle accelerators, improved gravitational wave detectors, enhanced cosmological surveys, may one day reveal clues pointing toward or away from string theory. Meanwhile, theoretical research continues. New ideas in holography, entanglement, entropy, and quantum gravity are expanding and refining the theory's reach. The future may also hold surprises. String theory might evolve into a broader framework that unites it with other approaches or discovers new principles that explain the landscape and selection of our universe. Importantly, the scientific process is never linear. Theories rise and fall, evolve and merge. String theory, with its immense depth, will likely shape the questions we ask and the methods we use for decades to come. Ultimately, the legacy of string theory is not just in answers it provides, but in the questions it inspires. String theory challenges us to rethink everything we thought we knew about reality. It teaches us that the fundamental building blocks of the universe may not be point particles, but tiny vibrating strings. That space and time might have more dimensions than we perceive. That gravity and quantum mechanics, once thought incompatible, might be unified in a single elegant framework. It shows us that reality might be more vast and varied than we imagined, possibly including a multiverse of countless universes with different laws of physics. It challenges our concepts of space, time, matter, and causality. It pushes the boundaries of human understanding into realms where intuition falters and only mathematics guides us. Philosophically, string theory reminds us that scientific knowledge is provisional, that our current theories, however elegant or successful, may be steps on a longer journey toward deeper understanding. It also illustrates the power and limits of human creativity, how we use imagination and logic to build models of reality far beyond everyday experience. But perhaps most importantly, string theory reflects a fundamental human drive, the quest for unity. The quest to understand how the myriad phenomena of the universe, from quarks to galaxies, fit together as parts of a coherent whole. This drive has shaped physics since Newton. It continues through Einstein. And now, in the form of string theory, it points toward a future where the deepest mysteries of existence may finally be unraveled. Whether string theory is ultimately the final answer or a stepping stone, its story teaches us to embrace wonder, to pursue knowledge boldly, and to remain humble before the vastness of the cosmos. In the end, string theory is more than a scientific theory. It is a testament to human curiosity and the unending search for meaning in a universe far stranger and more beautiful than we ever imagined.